So, welcome everybody to this week's problem set, which is paper session number 4, and will deal with the topic of voting. So, hopefully, in the lectures, you have seen some slides on this topic. If not, then you can see this presentation is kind of an introduction to some voting models. Okay, so actually, my plan was to talk about two papers. One theoretical and one empirical paper related to voting. But since I'm thinking that the presentation for the one paper that I'm presenting today uh, will be sufficiently long, I kicked out the other paper. Yeah, so we will talk about the Featherston and Pessendover paper from 1996 with the title "The Swing Voters Curse." Yeah, and I think you have seen something or you will see something like this in the lecture slides. So a model which is covered in the paper. Good. So let me briefly tell you what's happening in the paper. So the paper it's a theory paper, and it develops a theory of voting which explains absence of voting and role of even when voting is costless. So absence of voting means that people who can actually vote, so who are registered voters or who have like surpassed the age threshold to vote, that they do not go to vote if there are big votes, like voting for a new regime and this kind of stuff. And roll-off relates to a situation where if you are at the voting poll and there's several things to vote for, there could be several topics that you could vote for. Then some people only vote for some like issues and ignore other issues. So they partially vote basically. This paper tends to give an explanation to this like phenomena, even if voting is costless. And in addition, even if like the probability of being pivotal, so the probability of determining the outcome of the outcome of the election is very small or like zero, almost zero. What the paper does is that it shows the existence of a so-called swing voters curse. So a swing voters curse relates to a situation where less informed indifferent voters strictly prefer not to vote. Yeah, so they do not vote because they are less informed than other individuals in the society. And indifferent here relates to indifference between candidates who are available in the model. And surprisingly, this occurs even though like all the non-voters, also the voters in the model who stay absent, strictly prefer one candidate over the other. And this is not precise here. So what I mean by strictly prefer is that they believe with a high likelihood that one candidate is more appropriate than another candidate to be uh, to be more appropriate, basically. Yeah? So they believe with a high likelihood that given the state of the world, one candidate is much more appropriate to rule than another candidate. And this is quite surprising. So why wouldn't you then vote for this one candidate which you believe is kind of suitable for ruling the country or whatever? Um, so those are basically the kind of main results. And let's dig into the paper. So the starting point of the paper is to say that there's empirical evidence for, first of all, individuals who are being eligible for voting to stay absent. So people who can actually vote to not vote. So by not voting, I mean they don't even go to the voting poll, so they don't vote at all. Then there is empirical evidence for individuals who actually go to voting polls and that they do not vote with respect to all issues. This is called roll-off. And in addition, there is empirical evidence for individuals who are better educated and informed. So whenever individuals are better educated and informed, they participate at votes with a higher likelihood. Yeah, so they go to vote with a higher likelihood, and also they roll off with a lower likelihood compared to less educated and less informed agents or participants. And So the literature, it has been identified. It was kind of easy to identify why individuals who can vote do not vote. And the reason is like you can have heterogeneous costs of voting. So consider two individuals, and one of them has very high opportunity costs of voting. To going to vote takes like time to inform yourself, and it takes time to go to the voting poll. And you can think of an individual who has high opportunity costs of time. For him, the costs of voting are very high, and then there is another individual who does not have such high like costs of voting. And then you can easily explain why there are individuals who vote and others who do not vote by heterogeneous costs of voting. Yes, so a consequence of this is then again, some individuals vote and others do not vote, and it depends on their costs of voting. But if you consider this theory, it does not explain roll-off, because roll-off is like a situation. So this happens once you are already at the voting poll. Yes, so you already decided to go to the voting poll. And the idea is that the most costs related to the voting procedure itself are to get to the voting poll and to inform yourself ex ante. Yeah, so most of the costs related to voting happened before you went to the voting poll. Once you're there, the costs of voting should actually be negligible. Yeah, so they shouldn't be large or sufficiently large to prevent you from voting. Yeah, so this is an assumption, of course, but I think it's quite reasonable. So this paper, what it's doing is that it's basically building a theory which is in line with the empirical observations. So it does so by introducing asymmetric information into a simple model of voting. And the asymmetric information is modeled in the following way. Some voters have more information about the candidates and the state of the world than others. Yeah, so that's the basic idea. You can think of it as some individuals informing themselves in general much more, being more educated, and being capable of kind of more logically thinking about what would happen if a particular candidate would um, would be ruling in a particular state of the world. So they can reason in a much better way what the consequences would be if a particular candidate is in charge compared to another candidate than other voters who have less information. And by introducing this type of asymmetric information, the paper actually yields predictions which are in line with the empirical observations. And it's interesting that it does not depend on the voting costs and pivot probabilities. So there will be no voting costs in the model and pivot probabilities. So the probability that you actually have an impact on the outcome of the election is very small. So those are two things which in like models before this paper were saying that or were used to rationalize basically um, the absence of people who do not vote. Yeah, so the absence of voters was explained by voting costs and pivot probabilities. And here, this paper actually is still able to solve kind of the empirical puzzles, even when there are no voting costs in the model and if pivot probabilities are very small. And a consequence of this is that it rationalizes roll-off. Yeah, so not voting, even if voting is almost costless. Okay, so as I said before, roll-off is the situation where you do not have, like, almost have no, like, roll-off, like, refers to a situation where you do not vote, even though voting is almost costless because you already went to the voting poll. And the main mechanism in this model, it's kind of similar to something from like some result from or some paradox from auction theory, which is called the winner's curse. And it happens in auctions with interdependent valuations. So if you're not familiar with auction theory, auctions with interdependent valuations refer to situations where the goods which people can bid on, um, so people have valuations for the goods, but the goods, like the valuations, are correlated. Yeah, so the idea is like the classical example is there are kind of oil companies bidding on kind of a um, yeah, I don't actually know what the English term for it is, but you know they're bidding for fields where you can find oil. Yeah, and they're in order to find out about the valuations, they're drilling and taking samples from the old field, and obviously whatever you find due to your drilling gives you an estimation of how much value the oil field has to you. So if you want to bid for the oil field, this is something that you should consider. So your drilling sample or the results from your drilling is something that shapes your valuation. But in addition, the results of all the other individuals or companies which drilled and got their own samples should be also kind of determining your valuation. Yeah. So depending on what you get as a result, this should be correlated with what others are getting when they're getting their results. Yeah. So there is kind of correlation happening there. And the winner's curse now is describing a circumstance where the winner of an auction, who actually only bids according to his private information, is overbidding. So he's bidding more than the valuation that like the final valuation that we will have. So he's bidding more than the value of the product, like the actual value of the product for him. And the reason is that if the valuations are interdependent, so they're correlated, the only reason why he won the auction was because others bid less than him. Yeah. So he can only have one if others bid less than him. And the reason why others actually bid less than him is because they had lower valuations. Yes, so if a lot of other individuals have very low valuations, so their drilling samples really like had as a result that the oil field is quite kind of is not as valuable as your sample is saying, then this has a consequence also for your final valuation. Because condition on winning and only bidding with respect to your private information, you bid too much. Yeah, so you overbid it basically. And how can this problem be solved? Well, it can be solved by conditioning your bid on the state of the world when the bid is high. So when you are the high bid. So when you bid to um, kind of win the auction. And by doing this, you're basically controlling for situations where you bid high because you have found a high sample and you won, which means that others had less valuations than you. And since the valuations are interdependent, it means that you reduce your bid compared to a situation where you only bid according to your private information. And basically, as a result, the winner's curse will be solved. Yeah, so the idea here is that if you win in an auction with interdependent values, you should win by conditioning your bid on the state of the world if you win. Yeah, so you need to incorporate the information about the environment, so what other individuals are doing if you win. And by this, you solve the issue of the winner's curse. Now, in this paper, the authors are actually showing that something similar emerges in the voting model with asymmetric, so it's not election, of course, it's asymmetric information. And it's the so-called swing voters curse. Yeah, so a swing voter is a voter who determines the outcome of the election. Yeah, so depending on the behavior of a swing voter, the outcome of the election can actually change. Therefore, if you're a voter, your choice only matters if you are, so it's not the swing voter, but if you are a swing voter. So only if you are an individual whose vote can kind of change the outcome of an election, this is the only situation where your vote choice actually matters. So in all other situations, your choice doesn't matter because it cannot change the outcome of the election. So whether you vote or not vote, it does not change the outcome of the election. But the thing is that being the swing voter, um, it requires a particular state of the world. So So maybe, okay, let me, just for the terminology here, let's stick with the swing voter, but I think it's not 100% precise, but let's say if you're the swing voter, like in the slides that I'm showing you now, it means that you're pivotal. I think there is a difference between swing voter and so being a swing voter and being pivotal, but let's say now it means that you're pivotal because I think swing voter has a more general meaning. So let's say that a voter's choice only matters if he is pivotal, and being pivotal so returns so being pivotal requires a particular state of the world. So it requires a particular behavior of the other voters due to the information that they have. So you see here there is a similarity with the winner's curse in auctions with interdependent valuations. And the idea here is that a voter should now condition his voting behavior to the state of the world if he is the swing voter or if he is pivotal. Yeah, so if your choice matters, it is because other individuals have behaved in a particular way. And you should consider the behavior of other individuals when you are making a decision if your choice matters. That's the idea here. And yeah, that's basically what I said just right now. So the voter should consider the information of other voters when he is making choices because the information of other voters will derive the behavior of the other voters, and the behavior of the other voters will drive whether you are pivotal or not. So you should consider the information of other voters. And as we will see, the reasoning, this type of reasoning will drive the results in the paper. So we will have quite counterintuitive results in the paper in addition to like predictions which are in line with empirical observations. So let's start with the model. So the model itself is actually quite simple. So we have two states of the world, which are denoted by 0 and 1. So this capital Z here um, denotes the set of states. So states refer to, yeah, you can think of situations as, for instance, so what could be a good example? So a good example could be that think about climate change and think about the states of the world of being like climate change really happening and climate change not happening. Okay, so due to human behavior not happening. And depending on this set of states, there are parties which are kind of more capable of dealing with the issues. And so in Germany, for instance, you would say that the Green Party would be more capable of dealing with the issues to climate change than other parties. But if there is no climate change, then maybe it does not make sense to vote for the Greens. Yeah, so this is just an example. I'm not saying that obviously I'm a believer of climate change happening. So don't think I'm a skeptic here. But this is just an example. So those could be states of the world. Then we have two candidates, which we denote by 0 and 1 as well. Yeah, and this is made for simplification. And capital X here denotes the set of candidates. Furthermore, we have three types of agents, which are denoted by 0, 1, and I, and capital T denotes the set of agent types. And I will now explain you what those types are representing. So type 0 and type 1 agents are so-called partisans. So they are kind of hardcore fans of one candidate and they vote for the respective candidate of their type independent of the state of the world. So type 0 agents strictly prefer candidate 0 and type 1 agents strictly prefer candidate 1 independent of the state. So as a consequence, type 0 agents always vote for candidate 0 and type 1 agents always vote for candidate 1. Then type I agents are so-called independents, and their utility is state dependent. So given a state X and candidate Z, the utility is given by the following. So the utility is -1 if the candidate, so is kind of the value of the candidate is unequal to the state, and the utility is 0 if the candidate and the state are aligned. Yeah, so if the state is 0 and candidate 1 wins, then they have utility -1, or if the state is 1 and candidate 0 wins, then it's -1. And if the state and the candidates are aligned, then the utility is 0. So it's strictly larger. So they prefer candidate 1 and state 1 and candidate 0 and state 0. Yeah, so think of independence as being individuals who think if there is climate change, then I will vote for the Green Party. If there is no climate change, I will vote for the CDU, for instance, or some other party. Yeah, so this is the idea of independence. So their choice is state dependent. And partisans are hardcore people. So people who do not believe in climate change vote for other parties than the Greens. People who believe in climate change, whatever, they vote for the Greens. So let us talk about timing. So at the beginning of the game, nature is choosing the state, and the probability of state 0 being chosen is alpha, and alpha is between 0 and 0.5. And this is without loss of generality. Yeah, so it could be also higher. It's just made for simplifications. So in addition to the state, nature also chooses the set of agents by n plus 1 independent draws. So, and it's n plus 1 because we always, um, later, as you will see, when we're doing the analysis, we will always like make the analysis from the perspective of one agent, and then there are capital N other agents, and this simplifies the yeah, kind of the exposition of the results, and the derivations will be simplified if you think about capital N other agents than some really strange and odd kind of variable. Yeah, and nature is choosing the set of agents. And there is uncertainty not only with respect to the amount of chosen agents, but also to their types. Yeah, so whether they're partisans or whether they're independent. And here are the probabilities. So in general, the probability of an agent being selected. So being selected means that this agent can actually vote. Yeah, so if an agent is selected, he can vote, else he cannot vote. So the probability of an agent being elected is equal to 1 minus p of phi. The probability of an agent being of type of like independent, conditional on being selected, is then pi minus 1 minus p of phi. And the reason why we are dividing here, so why the authors have chosen this kind of um, this kind of way of modeling is because then if you multiply the probability of being selected with the probability of being of type independent, conditional on being selected, then the denominator here cancels out and we end up with pi. Yeah, so that's the reason why they have chosen this kind of way to model it. And type 0, so being of type 0, conditional being selected, is then p0 divided by 1 minus p of phi. And being of type 1 is then, yeah, p1 divided by 1 minus p of phi. All those probabilities that you see here are common knowledge, so everybody knows about the probabilities. So the type of an agent is private information, but the probabilities are common knowledge. So after the state and the set of the agents has been chosen by nature, each agent privately learns its type and receives a private message. And the private message is M, and its element is an element of the following set: 0, alpha, and 1. Whenever an agent is receiving a message 0 and 1, they are so-called informed agents, and they know the state of the world with certainty. So if they receive a message 0, they know for sure that the state of the world is 0. And the same holds for state 1. So if they receive message 1, they know for sure that the state is 1. And those are informed agents. The probability of being informed is equal to Q. And keep in mind that all informed agents receive the same message, yeah, because the message that they receive is the truth about the state of the world, and there would be a contradiction if there would be different truths about the state of the world, if all uncertainty is resolved. Now, agents who receive the message alpha, they're uninformed. And all that they have with this, like with respect to this message, is that they have a belief alpha about the state of the world being 0. So they believe that the probability of the state being equal to 0 is equal to alpha. Yeah, and they do not have any further information. That's why they're called uninformed, because they do not exactly know the state of the world, but they only have a probability distribution over the state of the world. Given all those preparations now with respect to showing you the model, we can now dig into the equilibrium. So let us talk about strategies. So what is a strategy? So a strategy of an agent is an element of the following set: phi, where phi denotes abstention, so not voting; 0, where 0 denotes voting for candidate 0; and 1, again, voting for candidate 1. The candidate who has a majority of votes wins the election. If there is a tie, each candidate wins with a probability of 50%. Now, let us talk about the particular strategies in a mathematical form. So a pure strategy is a mapping from the set of types and the set of messages into the strategy space. So your type and the message that you receive determine the strategy that you choose. Furthermore, we will consider mixed strategies, and a mixed strategy is a mapping tau, which maps from the type space and the message space into the 3-simplex. Yeah, so it determines a probability distribution over the set of pure strategies. And tau s denotes the probability of playing strategy S. For further notation, tau itself is a strategy profile, so it basically gives you the full probability distributions over the pure strategy set for an agent. Now the game is solved for symmetric Bayesian-Nash equilibrium. So symmetric means that all individuals who have the same type play the same strategy. Yeah, so there is no asymmetric, there's no consideration of asymmetric Nash equilibria here. So obviously, one issue could be that one is not considering equilibria which are also existent in this model. But I think, so I'm not sure, I think they do not talk about this in the paper. So maybe there are no, but then they're not talking about uniqueness in the results. Or maybe, yeah, they do not give any more insight. This could be also a reason. So the amount of agents which are selected varies from 0 to n plus 1. Yeah. And as a consequence of this, each agent can be pivotal with a strictly positive probability. So the probability can be very small, but it's still strictly positive. So every agent who actually kind of behaves strategically could end up in a situation of being pivotal. So let us talk about the actual strategies of the agents. So type 0 agents, they do not behave strategically because they always vote for candidate 0, independent of the state and independent of the message that they receive. Type 1 agents always vote for candidate 1, again, independent of the message that they receive and independent of the state. So they're not strategic. The partisans are not strategic, so you do not need to consider or analyze their behavior furthermore. Informed agents are voting according to the message that they receive. So it means that if they receive a message M, the strategy of them is to vote M. So if they receive the message that the state of the world is 0, they vote for candidate 0. If they receive the message that the state of the world is 1, they vote for candidate 1. Yeah, so independent informed voters always vote according to the message that they receive, and this again is not strategic. Yeah, so they do not consider the behavior of other individuals or other agents when determining their own voting behavior. Yeah, so also for them, they do not behave strategic. As a consequence, there is only one subset of agents whose behavior we need to analyze. So it should be 2 here. And this subset is given by the so-called uninformed independent agents. And I will shortcut them by UIA. So those are agents who are not partisans. So they want to vote for the candidate who is equal. So the candidate who is kind of appropriate for the state, and they are uninformed, so they only have a probability or a belief over the state of the world, and they do not know the state of the world with certainty. So let us introduce some further notation, which we will need in order to describe the equilibrium. So sigma ZC of tau is the probability that, there should be an X here, I'm sorry. Let's see, there should be an X here. So sigma Zx of tau is the probability that a random draw by nature results in a vote for candidate X if the state is Z given the strategy profile tau. Okay, so we fix a strategy profile tau for the uninformed independent agents. The behavior of all the other agents in the model is fixed. And then we're looking at what is the probability that a random draw by nature results in a vote for candidate X if the state is Z. Now, for a particular candidate X, only X partisans, should be no T here, and independents vote for X. Yeah, so partisans other than for candidate X do not vote for him. So the only ones are X partisans and the independents who could vote for X, of course. Therefore, we can explicitly write down this probability. So the probability that a random draw by nature results in a vote for candidate X is equal to the probability that an agent is actually a partisan of X, so they vote for X, and then it's the probability that an individual is independent multiplied with the probability that this agent is uninformed, and again multiplied with the likelihood that an uninformed independent agent is voting for candidate X. Yeah, so the tau here is kind of endogenous. And this is the probability if the state of the world is not equal to the candidate. Okay, so if it would be equal, then there would be another subset of agents who would vote for candidate X, and those are the informed agents who are independent. because they vote according to the states. So still we have the partisans voting for X, the X partisans, then we have the uninformed independent voters voting for X according to their strategy, and then in addition we have the independent informed voters who vote for candidate X, because now the state is equal to the candidate. And from the perspective of an uninformed independent agent, sigma x of tau is a correct vote, yeah, because this is a vote which corresponds to, so since like, even though they're uninformed, independent, like they're still independent, so they want to vote according to the state. So they want to vote for the candidate which is appropriate to the state, but of course they do not know the state. So this probability here is the probability of a correct vote, and sigma yx of t, so this should be y unequal to x. This is a mistaken vote. Okay, so this is a vote, so this is a probability of a vote happening for the wrong candidate. So for the candidate not being equal to the state. Now, in addition, we have sigma z of phi, which depends on the strategy profile. And this is the probability that a random draw by nature results in no vote for any candidate if the stage is Z given strategy profile tau. So this could also happen, of course. Yeah. So this is like if nature is drawing from a set of agents, it could happen that this agent is not voting for any of the candidates. So this happens if no agent is drawn. Yeah, so this can of course happen. Or if the agent who gets selected is not voting, who is staying abstained. And the only agents who might abstain are the uninformed independent agents, because the partisans, they will always vote, and also, so conditional on being selected, of course, and also the informed independent agents, they will also always vote. So they will not abstain from voting. So the thing here with respect to this probability is that both the probability of an agent being drawn and the strategy of an uninformed independent agent are independent of the state itself. Yeah, so the probability that an agent being drawn is simply an exogenous variable, and the strategy of an agent cannot be dependent on the state because the uninformed independent agents do not know the state. And as a consequence, the probability that in state 0, a random draw by nature results in no vote for a candidate, given tau, is equal to the probability that given state 1, a random draw by nature results in no vote for a candidate. And then we can simply drop the state here. And in particular, it's given by the following, so we can explicitly write it down. So it's first of all, obviously, the probability that an agent is not selected, which was then P of phi, if I'm not mistaken. Yeah, so this is the probability of not being selected. Then it's the probability of an uninformed independent agent to stay abstained, so not vote. Yeah, so which is here represented by tau of phi. So what will be crucial for the analysis is that we need to find the states of the world where the behavior of an agent, so of an uninformed independent agent, actually matters. Because those are the situations where his choices actually change the outcome of the election. So when is this the case? So this is the case when, so first of all, this can be the case if there is an equal number of agents who are voting for each candidate. because in this situation, then the outcome, so ignoring the vote of the candidate, so the agent that we're considering, um, the probability for each candidate to be voted is 50%. And if this agent votes for either of the candidates, he changed the outcome of the election because then one of the candidates wins with certainty. On the other hand, we have a situation where candidate 1 receives one more vote than candidate 0. In those situations, the agent can change the outcome of the election by voting for candidate 0, and then we have a tie, and the outcome switches from a certain win of candidate 1 to a 50-50 chance of both candidates winning. And the last point is then, again, basically the situation where candidate 0 receives one more vote than candidate 1. And then again, by voting for candidate 1, the agent can make the outcome be the outcome of a 50-50% kind of lottery compared to a situation where candidate 0 would win with certainty. And now what we will do is we will derive the probabilities for those states of the world. So we will start with the probability that an equal number of agents have voted for each of the candidates. So from the perspective of any agent, so actually from the perspective of any uninformed independent agent, the probability of an equal number, n, and n is now an even number, of other agents having voted for each candidate, and we denote this probability by pi t. T stands here for tie, and this depends on the state of the world, and it depends on the strategy profile of the uninformed independent agents. It's explicitly given by this expression here. And now you might ask yourself, so what this expression is representing. So it's basically all the possible, so it's going over all the possible constellations that obviously depend on the number of agents who are selected. And it's going to all those cases and creating situations where we have a tie. And if you want to kind of see how this expression is working, I think it makes sense if we briefly go through the sum here for different values of capital N, because this explains you, or this should give you some intuition on how this kind of sum is working. So let us go through this thing. So let me then just briefly or very quick write down again the sum here. So it's, oh, this is too thin. So it's pi of t depending on z tau, which is equal to the sum going from j equal to 0 to n divided by 2. And by the, so in faculty, I hope you're familiar with faculty, j faculty times n minus 2 times j faculty times sigma phi of tau by the power of n minus 2 times j times now sigma z0 tau times sigma z1 tau by the power of j. So let us go to the sum for different values of capital N. So let's start with the most obvious case, so capital N being equal to 0. So this would refer to a situation where nature, apart from the one agent, has selected 0 other agents. So in this case, what do you think should be the probability of an equal number of other agents having voted for each of the candidates? So it should be equal to 1 because nobody voted for any candidate. Okay, so let's go to the sum. So the sum is then simply going from j equal to 0 to 0 of 0 faculty divided by j faculty times j faculty times 0 minus 2j faculty times sigma phi capital, so tau 0 minus 2 times j times, yeah, we can copy this one here. Yes, let's just put like this here. And if you calculate this, what do you get? So this sum only has one term. So it's 0 faculty divided by 0 faculty times 0 faculty. So j is now 0 times again 0 minus 2 times j is now 0 faculty times sigma phi tau by the power of 0 times, now again we substitute this expression here, by the power of 0. And now 0 faculty, this is equal to 1, this is equal to 1, this is equal to 1. So the probability of an equal number, so the probability of 0 other agents having voted for each of the candidates is equal to 1, obviously, because there are actually no votes for the candidates. Okay, so this is like one example. Let us go to the next example. Let me just delete everything here. And we can leave this there, that's fine. So now let's go to n equal to 2. So what will change? We'll have changes here, 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 and that's it in here, I think, yeah. So now we have a 2 here. So 2 divided by 2 is equal to 1. So we have two terms. Then here we have 2 faculty. Below we have 2 minus 2j. And then here we also have a 2. So if you now go through the terms, what we have is, so the first term is when j is equal to 0. So we have 2 divided by, again, 0 faculty times 0 faculty times 2 minus 0, so 2 faculty, which is then again 2, times sigma by the, so sigma phi tau 2 minus 2 times 0 is 2 times, and then the last expression falls away. So basically what is remaining here is only this expression. So this is the likelihood that an agent is not drawn by the power of 2. So if there are 2 other agents, then how can this be equal to a situation where both candidates have received an equal amount of votes from 2 candidates? Well, one possibility is that both candidates, both agents are actually not selected, because then there are no votes for the candidates. Okay, so this is the first situation. To this, we obviously add some other possibility, which is then 2 faculty divided by, now j is equal to 1, so 1 faculty times 1 faculty times 0 faculty times sigma phi tau by the power of now 0 times, now we can again copy this here by the power of 1. So we simply erase the exponent there, and then this is equal to sigma phi tau by the power of 2 plus 2 times sigma z0 tau times sigma z1 tau. So the first term again refers to a situation where 2 agents who are in the set of agents are not selected. So there is an equal amount of votes for each of the candidates because both receive 0. And then the second term here refers to a situation where both agents get selected, but one of them is voting for candidate 0, which is this probability here, and the other agent is voting for candidate 1, which is this probability here. And this can happen 2 times because we can interchange the agents. So one time one of them is voting for 0 and the other is voting for 1, and then we switch the roles. This is why we have the 2 here. And yeah, this is just to show you how this kind of expression is working. So it's basically going to all the possible cases where we would have an equal number of votes for the candidates. Okay, so yes, I think then this should be clear. So we will need this. And then there is also the probability that from the perspective of an agent, from uninformed independent agent, the probability of candidate X having exactly 1 vote less than candidate Y, which we define by pi x of z of tau. Again, this depends on the state and the percentage profile. And this is given by this expression here. And yeah, you can, if you want to understand why it's this expression, then you can go simply to the cases again that I showed you before. I will not do it again because it's quite similar to what I showed you in my writings on the slide before. So then this is referring, so this probability is referring now to the 2 events here, whereas the first probability was referring to the state, to the kind of state here. Yeah, and why do we need all of those probabilities? Well, I told you before that the choice, so if an agent is pivotal, so if an uninformed independent agent is pivotal, it is just because there is a particular state of the world, and for those particular states of the world, we need to know what the probabilities for them to occur are actually. Yeah, so those probabilities that you see here and here, they are basically the pivotal probabilities. So they summarize, so in a summary, they represent the pivotal probabilities of an agent. So given those probabilities, what we now can write down is kind of the expected utility differences between the strategies that an uninformed independent agent has. And we will define it by EU, so this stands for expected utility. So it's the expected utility of strategy X given that the other agents are playing some fixed strategy profile tau. Yeah, so we're fixing this strategy profile. And the set of strategies for an uninformed independent agent is 0, so voting for candidate 0, voting for candidate 1, or staying absent, which is then phi. And we'll now write down the differences between the expected utilities for the different strategies, because this will be used to determine the equilibria. So first, what we have is the expected utility of voting for candidate 1 minus the expected utility of staying absent. Second, we have the expected utility for voting for candidate 0 and the expected utility of staying absent again. Finally, what we have is the difference between strategy, so the expected utilities of strategies 0 and 1, and it's given by this expression here. Yeah? So I will not go into the details of those expressions. This should be quite straightforward here. So yeah, if you compare them with the probabilities that I introduced before, it should become clear what those expressions actually are. Yeah, so some things cancel out, but at the end of the day, they will determine kind of what the equilibria outcomes will be. So given those differences, we can kind of state the first result, and it's summarized in proposition 1, and it's the following. So let the probability of an agent to be chosen be strictly larger than 0. So I think this was just a second. I have to check this again. So P of phi was the probability of an agent not being selected. So let there be an amount or an expected amount of agents who are not elected be strictly positive, and at the same time, let's assume that there are some informed agents. So Q equal strictly larger than 0 refers to the probability of some of the independent agents to being informed is strictly larger than 0. Let's assume that there are at least two agents, and let's say n is even. Yeah, this is also without loss of generality here. Now, for any symmetric strategy profile tau, in which no agent plays a strictly dominated strategy, so not playing a strictly dominated strategy means that you do not play a strategy which is inferior to another strategy for all the states of the worlds that are possible. So here is state 1 and 2. If we have the following situation, so if we have the situation that the expected utility of voting for candidate 1 is equal to the expected utility of voting for candidate 0, which means that this agent is independent of voting voting for candidate 1 or 0. This implies that the expected utility of not voting, so staying absent, is strictly larger than the expected utility of voting for any of the candidates. So that's quite a nice, like, counterintuitive result. So it's basically saying, so it's basically the or kind of reflecting the swing voters curse in the model. So what it's basically saying that if you, as an uninformed independent agent, if you are indifferent between any of the candidates, then what you should do is you should not vote. Yeah. So there's kind of this quite interesting result if you think about it. So you're indifferent between the two candidates, and this implies that you should not vote. And a consequence of this is that when we later consider the equilibria in this model, we will see that there is no equilibrium where an uninformed independent agent mixes between both candidates. Yeah, because for mixing, you need to be indifferent between all your strategies. But what you see here is that once you're indifferent between pure strategy 1 and pure strategy 0, a consequence is that the expected utility of not voting is strictly larger. Hence, you cannot be indifferent between all your pure strategies. And the consequence is there is no equilibrium where you mix between both candidates. So the only type of equilibria which are possible are pure strategy equilibria. So equilibria where you vote for one of the candidates with certainty, or mixed strategy equilibria where an uninformed independent agent mixes between not voting and voting for a single candidate. Yeah, so this is kind of proposition 1 um, is kind of restricting the sets of possible equilibria that we need to consider in this model. Okay, so let us build some intuition with respect to proposition 1. So now, given that an uninformed independent agent is indifferent between voting for candidate 1 and voting for candidate 2, what we get, if we now consider everything from the perspective of voting for candidate 1, we can substitute here E of U of 0 of tau because it's equal, but we're just doing it for 1 now. What we get is this expression here. And what the result of proposition 1 is that this thing is strictly larger than 0. And the reason is because each of those differences here is strictly larger than 0, strictly smaller than 0. Yeah, so it's so this should be strictly smaller, of course. And the reason is that, so the reason why those differences are strictly negative is because the informed independent voters vote for the correct candidate in each state. So what are the differences exactly reflecting? So the difference here, let me just erase some of the stuff. So what is the first difference here? So the first difference here, so the first term is the probability. Let me just check again that I'm 100% sure. So that's the probability that candidate 1 gets exactly 1 vote less than candidate 0 if the state of the world is equal to state 1 minus the probability that candidate 0 gets 1 vote, exactly 1 vote less than candidate 1 if the state of the world is equal to 1. And the reason um, why this difference is negative is that because all informed independent voters vote for the correct candidate in each state, it is much more likely that you are pivotal in this situation here than in this situation. Because with a higher likelihood, actually candidate 1 will win if the state is 1, then in candidate in states then when then candidate 0 basically. Yeah. So in state 1, candidate 1 will win with a higher likelihood than candidate 0. And as a consequence, the likelihood that you are more pivotal is basically in this situation here. Yeah. So you are the likelihood that you're pivotal is higher when candidate 0 is considered than candidate 1. And the same holds for this difference here. This will be also negative. And what is the idea here? So the idea here is that why is this strictly negative? So what's the intuition behind this? Well, the idea is by staying absent, so by not voting, the uninformed independent agent minimizes the likelihood that he votes incorrectly. Okay, so this is kind of the reason why an uninformed independent agent rather relies on informed voters informed independent voters to vote for the correct candidate. So since he does not know the state of the world and he knows that he could mess up by a wrong vote something in so he could by a wrong vote he could mess up the situation in the states of the world which are aligned with the candidate. He simply decides to not vote at all and relies on the informed independent voters to vote for the correct candidate. Yeah, so that's the reason why the agent is staying rather absent than um, than uh, than voting for either of the candidates, just to make sure that he minimizes the likelihood of voting incorrectly. Yeah, so that's the intuition behind proposition 1. So as I said before, proposition 1 is restricting the set of equilibria that we need to consider. And for the further analysis, what we'll do is we will consider so-called large elections. So large elections refer to situations where we have a large potential, so a large number of potential voters, so a large number of capital N. And just for notation, we will have a sequence of games with capital N plus 1 potential voters. And the games are indexed by capital N. So if there is a game with so indexed by capital N, it means we have capital N plus 1 potential voters. And there is a sequence of strategy profiles for each game, which is denoted by this sequence here. Yeah, so each tau, and if you have a superscript of capital N, is referring to the strategy profile for the game with N plus 1 voters. So before we come to the main results, we have some intermediate results which help us to prove the main results of the paper. So here what we have is that let's assume, so this is lemma 1. So let's assume that the probability of some individuals being of independent type times the probability of some of the individuals being informed being strictly larger than 0. Basically, this means that both terms should be strictly larger than 0. And let's say alpha is simply strictly between 0 and 1, which means that we consider situations where we actually have uninformed agents only. Yeah, so we only consider situations where we have where the uninformed agents are actually uninformed. Yeah, because if alpha would be equal to 0 or 1, then they would be informed because they know with certainty what the state of the world is. And next, let's consider a sequence of voting games and strategy profiles described by this sequence here. Then we have the following. So if there exists a lower boundary for the following difference, so the difference between a mistaken vote for candidate X if the state is Y minus the probability of a mistaken vote if for candidate Y if the state is X. If there exists a lower boundary for this difference, which means basically that the probability that there is a mistaken vote in state there is a mistaken vote for candidate X in state Y. So basically it means that if we have either of the two situations, so if this, so sigma 0, 1 tau n minus sigma 1, 0 tau n, if this is strictly larger than epsilon. So if there is a higher likelihood for a wrong vote or an incorrect vote to emerge in state 1 for candidate 0 rather than in state 0 for candidate 1, for any amount of potential voters, and obviously if the state and the candidates are not equal to each other, then what we have is we have a threshold, an upper bar, so a threshold, a lower threshold of potential amount of agents, such that if we have more agents than this threshold, it holds. So for all the uninformed independent agents, it holds that the expected utility of voting for candidate X is strictly larger than the expected utility of staying absent and the expected utility of voting for candidate Y. So basically what it's saying is that if the probability for a mistaken vote is larger in state 1 than the probability of a mistaken vote in state 0, then all the individuals, so all the uninformed independent agents, should vote for candidate X. So this would be candidate 1 then. And the second result here is an implication of basically it's a direct implication from the first result, lemma 1. But it's not so interesting for the remaining parts of the paper. So I will just give you an intuition for the first part. So let's consider state 1. So we're now considering lemma 1.1, and lemma 1.1 has the following intuition. So from the perspective of state 1. So if the probability that a random draw results in a mistaken vote in state 1 is larger than the probability of a mistaken vote in state 0, so this would be basically what I told you before. So sigma 1, 0 tau n minus sigma 0, 1 tau n. So if this is strictly larger than some strictly positive number, then the conditional probability that the state is 1, given that the agent is pivotal, goes to 1 if capital N increases. So basically what this thing is saying is that if with a higher likelihood a random draw results in a mistaken vote in state 1 than in state 0, then you know with certainty that you are in the agent knows with certainty that he is in state 1, given that he's pivotal, if the amount of other agents is very large. Well, the reason for this is that the agent can only be pivotal if there are enough or sufficient informed agents who are making the correct decisions to compensate for wrong decisions made by the uninformed independent agents. Yeah, keep in mind that the assumption was that the likelihood for a kind of a wrong vote, so vote for candidate 0 even though the state is 1, is higher in state 1 than in state 0. So this means that if I am pivotal, it can be only because a lot of informed voters have been voting for candidate 1, and they only do this if the state is 1. So I know that if I am pivotal, the likelihood that I'm in state 1 is higher than the likelihood that I am in state 0. And now if we increase the amount of agents more and more, I become more and more certain that the state is 1 if I am pivotal, because there are more and more informed agents actually needed for me, like, to be actually pivotal. Yeah, and this, like, if you increase the amount of agents more and more, this basically gives you certainty. So this is why we consider large elections, and that's an interesting result actually, if you think about it. So you are more likely as an uninformed independent agent, given the assumption that we made in the beginning of lemma 1.1, you're more likely to be pivotal in state 1 than in state 0, which means that this gives you an information about the state. So just being pivotal gives you an information about the state because of the behavior of the informed agents. Yeah, and this is the analogy of the to the winner's curse here, because there, once you are having the winning bit, it is because of the behavior of others and the information that you have. And here in the voting model here, you are only pivotal because the informed voters or informed agents received some piece of information that they are in state 1 and voted accordingly. And you using this information to to determine your own behavior. And if you know that it's more likely that you're pivotal in state 1 than in state 0, and you are actually pivotal, so this is the only situation where it matters what you choose, then you should vote for candidate 1, because again, you are an independent voter and you want to vote according to the state. So as a consequence, you strictly prefer to vote for candidate 1 rather than staying absent, and you would rather stay absent than voting for candidate 0. Yeah, and this is basically what's reflected here. And that's by itself a quite nice and interesting result. Yeah, so it's kind of pinning down the analogy to the winner's curse in auction theory. So I think I mentioned most of the points here. Let me just check real quick. So yeah, since the uninformed independent agents do not know the state of the world, yeah, they want to maximize the probability that the informed independent agents decide the election, because yeah, basically um, they do not know the state with certainty, but they rely on the behavior of those who know the state with certainty to determine the outcome of the election. And what they want to actually do is they want to vote in order to compensate for the partisans who vote independently of the state. So, in basically, you could, like, in principle, what you could think of is that the partisans, they are just strictly voting for one candidate independent of what the state is, and this is not maximizing the utility of the uninformed independent agents, because the partisans simply vote for one candidate and do not care about the state. But the utility of the independent agents does. And what the uninformed independent agents then do is they kind of help or add votes to the votes of the informed independent agents such that they decide the election, and this maximizes also the utility of the uninformed independent agents. And yeah, that's basically the reason why those individuals would vote. So they vote to compensate for the partisans. And what we will do now is we will come to the actual equilibrium behavior. So we will come to actual equilibria. So far, we will just restricting the set of equilibria and deriving results which would help us for the rest of the results. But now we will actually come to the equilibria outcomes of the model. So suppose, so this is proposition 2. Suppose that this condition here holds, so those conditions here hold, which are basically saying that yeah, we have informed individuals, and it's also saying that the mass or the number of independent uninformed agents is relatively small to the mass or the number of partisans in the model. This is reflected here by the difference and putting a absolute terms over it. In addition, this condition, last condition here, is saying that the likelihood that the likelihood that some individuals do not, or not, some agents do not get selected is larger than 0. So there are some agents who do not get selected. And so if those conditions hold, what we have is the following in large elections. So if the first part of proposition 2 is if the amount or the number of partisans of candidate 0 is much larger than the expected amount of independent and uninformed voters and of partisans for candidate 1, then if we increase the amount or the number of agents who are eligible for voting more and more, the consequence will be that the uninformed independent agents will vote for candidate 1 with certainty. Okay, so if there are many 0 partisans, and if there are in general many eligible agents, a consequence will be that all the uninformed independent agents will vote for candidate 1. The same thing holds when the amount of candidate 1 partisans is very large compared to the expected amount of independent and uninformed voters and to 0 partisans, because then if we increase the amount of eligible agents more and more, a consequence will be that all uninformed independent agents will vote for candidate 0. So as a consequence, proposition 2 is saying that if we are dealing with circumstances where the expected amount of partisans, so any of the partisans, is relatively large compared to the expected amount of uninformed independent agents, those agents will actually play a pure strategy and vote exactly for one candidate. And they do this exactly for what I mentioned the slide before, to compensate for the large amount of partisans. Yeah, so they compensate for the large amount of partisans because if they wouldn't do this, then the informed independent agents wouldn't be able to determine the elections because the amount of partisans is simply too large here. And the very interesting thing here is that they do this independent of their prior belief alpha. So what does this exactly mean? So basically it's telling you that if alpha is very close, so if alpha is very close to 1, we just check what it exactly was. So if alpha is very close to 1, it means that, oh, I just lost it. Ah, yeah, here. So if alpha is very close to 1, it means that the uninformed independent agents believe with a very high likelihood that the state is 0. And do not forget that nature is drawing the state according to this belief. So they are correct with their belief. So if the belief is very close to 1, it means that actually nature, with a high likelihood, has drawn state 0. Now, proposition 2 is then still saying that independent of your belief, so let's say alpha is equal, to 0.99999, something like this. So the uninformed independent agents are very certain that the candidate that should be voted is candidate 0. So now, interestingly, the first result here is still saying that if the amount of 0 partisans is very high, then if we increase the amount of agents, of eligible agents, you should still vote for candidate 1. That's a very counterintuitive result. Yeah, if you think about it, that's a very counterintuitive result. So just imagine you are very sure that one particular candidate is eligible for being in charge, and you still do not vote for him just because there are a lot of partisans of this candidate in the economy, in the model. But this is the equilibrium outcome. Yeah, this is an equilibrium outcome, which means that there is no incentive to deviate independent of what the value of alpha is. And that's a very interesting result if you think about it. So this is kind of a concept, like this is strategic voting basically. This is like if people do not vote according to what they believe and what their preferences are, okay, they vote, but in this model they also vote according to what their preferences are. But you can get results like this if people or individuals vote strategically. Yeah, so you are sure that one candidate is eligible, but you still do not vote for him because there are a lot of partisans, so people who are hardcore fans for him. And this is a consequence of asymmetric information. Yeah, if there wouldn't be asymmetric information, you wouldn't have this outcome basically. Now let us come to the other case. So let's assume that the amount of uninformed independent agents, the number reflected by this probability measure here, is larger than the expected amount of partisans for one of the candidates. And then again, we consider a sequence of strategy profiles. And what we then have is we have 3 types of equilibria in this case, depending on whether the amount or the expected amount of 0 partisans is higher than the expected amount of 1 partisans, or the other way around. And what we have is that if the expected amount of 0 partisans is strictly larger than the expected amount of 1 partisans, and there's a large expected number of uninformed independent agents, then the uninformed independent agents mix between voting for candidate 1 and not voting, which means that they either vote for candidate 1 or they do not vote at all. But as I said, they don't vote for candidate 0. And the reason for this here, so why they're mixing here, is that they want to offset, they want to partially offset the 0 partisans, which are simply voting for candidate 0 independent of what happens. But since there are a lot of uninformed independent agents, what they still want to make sure is that they do not vote for one candidate too much, because then they could determine the outcome of the election, but they still want the informed independent agents to determine the outcome of the election. So they only want to compensate partially for the large amount of 0 partisans in the model to make sure that the informed independent agents actually determine the outcome of the election. And that's why they mix between voting for candidate 1 and not voting. So if all of them would vote for candidate 1, then an issue could be that so many of them voted for candidate 1, but the state is 0 and the informed agents cannot win the election, which would be bad also for the uninformed independent agents. So that's why they mix between voting for candidate 1 and not voting. Because if the state would be 0. So why don't they vote for 0 at all? So if the state would be 0, there would be a sufficient amount of 0 partisans and informed independent agents who would vote for 0 to determine the election. Yeah, so that's why they don't put any probability mass in voting for candidate 0. The same thing holds for the second point here. And then in addition, if the amount or the expected amount of 1 partisans is equal to the expected amount of 0 partisans, which is reflected by this difference being equal to 0, then the uninformed independent agents do not vote. And the reason is simply because if you have an expected amount of agents for the like partisans being the same, then the informed independent agents will with certainty determine the outcome of the election, because they will simply add up to the equal amount of votes for of the partisans for each of the candidates, and hence the uninformed independent agents do not need to vote because their utility will be maximized even when they, so especially when they do not vote, because if they would vote, then they could again affect the outcome of the election in a wrong way. And that's actually the those are the main results of the paper. So what proposition 3 is showing is that when there is a sufficient number of uninformed independent agents, then not voting will occur in equilibrium. Yes, so if the amount of agents is large, so eligible agents, which means that if you have a sufficient amount of potential voters in your economy, in your country, which should be certainly fulfilled in most countries, and if you have a sufficient number of individuals who are independent and uninformed, then the model predicts that not voting will occur in equilibrium. And the interesting thing is that this occurs even though there are no costs of voting. So we did not put any costs here in this model. So there are no costs of voting here. And even if the probability of being pivotal is very small. And the reason for the pivotal probability being very small is we consider large elections, so very large amounts of capital N. So the larger the amount of agents or eligible agents, the lower the probability that you are pivotal. And in this limit, actually the pivotal probability will be very close to 0. And this actually rationalizes roll-off, because roll-off refers to a situation where you do not vote if you are already at the voting poll and if you are already at the voting poll and do not have any cost at all. And in this model, we are basically not only saying that not voting will occur in equilibrium if there are no costs, but also if the pivotal probability is very small. So even if you know that your behavior will unlikely change the outcome of the election. And what the paper then does is to proceed and show that the electoral outcome actually does not depend on the assumption of incomplete information. So this is a side result, which is also quite interesting, because you might then think that, so as a think about a government which is thinking about whether it should make the uninformed independent agents to informed independent agents by education, by, I don't know, informing them and so what. Because if everybody would be informed, then the utility would be based, so from a welfare perspective, utility would be maximized if everybody would be informed. So if everybody would know what to vote for. There's no uncertainty related to this, because as long as there is information asymmetry, what will happen is basically there is a likelihood that one kind of outcomes occur. So a likelihood that uninformed independent voters like make wrong decisions. And now what the paper is doing is that it's defining kind of an information aggregation here in saying that an election mechanism is fully aggregating information if the electoral outcome is the same under private information as it would be under perfect information. So this is now saying that um, if so in perfect information we would almost surely have desirable outcomes of the election. So because everybody would then, if there's kind of if there's known information, so if I know what the others are doing and I know their preferences and everything else, then there are election mechanisms which are maximizing kind of welfare with respect to the outcome of the election. Another question is, so we're saying that an election mechanism, which now in our case is an electoral mechanism, which has uncertainty that it's fully aggregating information, so it's basically yielding the same outcome as a perfect information election. Um, so this is perceived to be something good, basically. You could think of it like this. So if you are fully aggregating information, it means that you minimize the amount of mistakes or like wrong votes which are made in this model. And now proposition 4 is actually saying that even if we have private information, so I will just stick to my intuition. So even if we have private information, if we have large elections, what we will have is that the outcome of this private information model will be such that the correct candidate wins almost surely. So it means that candidate 1 wins if the state is 1 and candidate 0 wins if the state is 0. Yeah, so uh, basically this is saying that independent of whether there is private information or perfect information, if we have large elections and we're using this election mechanism in the sense that the candidate with the most votes will actually win, then in both cases we will like have an outcome where the correct candidate wins. So it means that welfare is kind of maximized in this situation. Of course, it depends on the number of partisans in both scenarios that we're considering, but fixing them kind of the correct candidate should always win because it maximizes the utility of the independent, uninformed, and informed agents. Yeah, so think about it like this. And yes, that's a nice result because it's saying that it's not such a huge of a problem if there is private information, as long as there are sufficient eligible agents in the country which could potentially vote. And yes, this brings me to the conclusion. So what did we find? So like one of the results was that so the paper basically rationalized staying absent and rolling off, even if there are no costs of voting and the probability to be pivotal is very small. So this was reflected in proposition 3. And this is quite a nice and counterintuitive result comparing it to previous literature. So previous literature with respect to this paper here, of course, because before the theory was about heterogeneity of cost, and now we have a theory of asymmetric information which can yield like even more predictions or can match more the empirical observations than previous literature. And it also showed, so this was proposition 2, that under some circumstances, the uninformed independent agents vote for a candidate even though they are almost certain that the other candidate is the correct one. Yeah, so this was reflected by proposition 2. So even though an uninformed independent agent knows that with a very high likelihood this one candidate is actually the one which maximizes my utility, I will still vote for the other candidate. And the reason was because there are a lot of partisans for this particular candidate. And they want to offset the amount of partisans in order for the informed independent agents to determine the election. And finally, what I showed you the slide before is that even if there is private information, if we consider large elections, the correct candidate will win. So private information is not that big of an issue if we have large elections. And those were the main results of the paper. And this finishes this week's problem or exercise session. So then see you next week.